Hey, chemistry. I just wanted to take a minute and walk you through the electromagnetic radiation spectrum. We have talked about it a little bit. We've used it a little bit. We have even drawn it out a little bit, but I really want to take a look at the whole spectrum and show you kind of the gamut of possibilities that's there. So I found this first graphic that I really like because it shows you how the size of the wavelength, is related to objects that we're familiar with. So you can kind of wrap your brain around how big or how small these actual waves are. So we'll start in. Let's just start on one end. So you can see over here on this end, we have frequency here, and then this is supposed to be like a graphic of wavelength, even though they don't have an actual wavelength like present. And so our really long wavelengths, which is very low frequency, those wavelengths are really, really long. They are on the scale of like buildings. They can even be on the scale of a country. My grandpa used to be really into, well, he was into uh, radios that you could build yourself and then you could communicate to people around the world. And he lived in Michigan, and he actually couldn't communicate with anyone in our country except for people on the West Coast, because the wave was so long it would actually go up and it wouldn't touch again until like California. That's how long it was. It would just skip over the middle of the country entirely and wouldn't actually touch down until way over on the West Coast, way over compared to Michigan, right? And it was pretty incredible that he could actually talk to people in California, but nobody in between, because his radio wave was so long. So that is one of our longest waves, and those tend to be radio waves. Now, as we move this way, we tend to, our wavelength, you can see, gets shorter and shorter until this other end where it's very, very short. And then our frequency gets higher and higher. We get more and more waves. So on this end of the spectrum, we have gamma rays, and those are some of our shortest waves, and they're on the order of an atomic nucleus. So gamma rays, the length of a gamma ray is actually about the same length as an atomic nucleus, which actually does some really cool things when you start looking at shooting some of these rays through atoms or through crystals, because the wavelengths and the diameters of the nuclei, or the spaces in between them, they tend to line up. So it's kind of a cool effects once you get there in your science life. And then you can see some of the other things in between. So here we have microwaves, and microwaves can be about the size of a human. They get smaller and smaller. They can be about the size of a bug. When you get to infrared molecules, they tend to be as small as the point of a needle. So pretty small, but still visible to our human eye. When we look at visible light is very, very tiny. We tend to measure it in terms of nanometers, and it's about on the size of like bacteria, or maybe a little bit bigger than bacteria, like a protozoa. So you can't see bacteria or protozoa unless you look under a microscope and you stain them the right way. If you take microbiology with me, we'll actually look at protozoa from local water supplies. We'll stain bacteria that we grew ourselves, and we'll look at that. And you can see, even when they're magnified under like 1,000 times, they're still really, really, really tiny. And that is about the order of a visible light wavelength. That length could be seen under a high power microscope that's multiplied thousands of times. Otherwise, we can't see it with our human eye. Ultraviolet radiation, on the other hand, is so small you couldn't even see it under a microscope. It would be about the size of a molecule. So, in order to look at molecules or atoms, which line up with about the length of an X-ray, you can't even see those with microscopes. You have to look with something called an electron scanning microscope. And the images on an electron scanning microscope, you're not actually seeing directly with your eye, even magnified through bending light through glass. What you're actually seeing in an electron scanning microscope is they hit these objects with radiation. The radiation bounces back to sensors, and a computer reads those reflected images, and it actually builds the image of the molecule that you're looking at. So ultraviolet radiation, X-ray radiation, you can't even see with magnification. You actually have to kind of infer it from reflected radiation, which is kind of cool too. So it gives you a little bit of an idea on how big these waves are that we're talking about. Our lab we're about to do is going to be done with visible light. And so we will be dealing with light around this area of the spectrum. The second graphic that I have for you, I also like this because it just shows you options. Like, okay, so we have all of this radiation. What is it actually used for? So here you go. Here's a lot of examples on the bottom. Again, we have our longest wavelength to shortest. We have our low frequency to high frequency. So it's set up, this spectrum is set up exactly the same way as the spectrum we just looked at. And you can see what they're all used for. Some of these really long wavelengths are used for communication in earthen subways, AC power, certain monitors, certain radios, TV. By the time we get around here, we're dealing with microwaves. So your cell phone, microwaves, and satellite, those are all microwaves. Visible light, infrared, ultraviolet, we have lots of uses and consequences of those as well. I mean, infrared, you've heard of like infrared technology or infrared goggles. Visible light obviously is really important to us. Without it, we couldn't see things. Ultraviolet starts to get into some of the damaging radiation. You can see up here, this side is ionizing, and actually in our lab, we're going to be calculating energy off of visible light that we see, and you'll see the pattern as wavelength and frequency changes. You'll see the pattern in how energy changes also. And so ultraviolet can get into things like food sanitation, but it can also get into things like damaging our skin. And then X-rays, we've all either had an X-ray or known someone who's had an X-ray or been familiar with what they're used for. And then gamma radiation, actually the majority of gamma radiation that we know of comes from space. All of this radiation actually pummels Earth every day and comes in through space. But we can also create some gamma radiation on Earth too. Okay, so hopefully you feel a little bit more introduced to the electromagnetic radiation spectrum. If you have questions, let me know. Otherwise, I will see you in class.